Hey guys, welcome back to BMES's Tech Workshops. Obviously, due to COVID-19, we cannot meet in person, so this will be our first virtual MATLAB workshop. So that the way that this is going to work is that the four of us have broken up MATLAB topics into what we deem as very important, and I'll be doing the first part of it.
So if you feel like you need to refresh on your MATLAB at all, there are two resources that we have here for you. The first one, MATLAB OnRamp, is a tutorial that takes about 45 minutes to complete. If you've taken BioE 201, then you may have already taken this. It just basically goes over syntax and basic uses and functionality of MATLAB. If you're looking for more specific help with, like, for example, a function or something that you don't know how to use, you're going to want to turn to MATLAB documentation. It's very thorough, it's very good, and it has just about all the information you could ever need to use anything on MATLAB. So if you would like to go through and review any of these, feel free to pause the video now, and if not, we will then continue.
All right, so for the first part, we're going to be focusing on integration manipulating ordinary differential equations. So for the first part of our challenge, we are going to integrate this lovely function over here in between 0 and 10. The first objective is to graph the function in between the bounds and then to find the final numerical value of the integral. So pause the video now to do this by yourself and then click continue to see the solution. All right, so this is a solution for the first part of our first challenge. On the right, you see our wonderful graph, which should kind of look like an exponential increase. And then on our left side is the code to solve this. So the way that I approach this is by creating a symbolic variable x, which is kind of our independent variable. And I constructed a function, a variable fun, which is the function in terms of x. The third line over here is the integral of our function in between 0 and 10. And then the fourth line is displaying the numerical value. And then fplot graphs your symbolic functions. And fplot is specific to like symbolic functions and symbolic variables. All right, so for our second part of challenge 1, we're going to find the solution for this differential equation, given the initial condition. So pause the video now to do it by yourself, and then click continue to see the solution. Welcome back, and this is the solution to the second part of challenge 1. Here we started off with something that we've done in part 1. We created a symbolic function, y of x, in where y is a dependent variable of x. Second line shows an ODE structure. So since x is already declared an independent variable, your diff y of x, which is the derivative of y in terms of x, is the dy dx from this part. So here we just initialized our differential equation. The third line is sending a condition variable. It's saying that y of 0 is 5. You're going to have to use the double equals just because this is a symbolic function. And then in order to integrate this variable dependent function, you're going to use the function dsolve. So this one is taking an input of your function and then your initial condition. And then the last line is just displaying your final solution.
So for this portion of the workshop, we'll be going over the fast Fourier transform in MATLAB and how we can use it. So what we're going to be doing first is going over an example, just showing how to do the transform and how to visualize it and how to find the underlying frequencies within a signal. And then after that, we're going to be using an actual audio file and then finding the underlying frequencies within there. So just a brief background on the Fourier transform. A Fourier transform is a process that locates the frequencies within a signal. So for example, if a signal is playing at 100 hertz, it's going to look like a sine wave when you graph it over time, but the Fourier transform is going to show a massive spike at the value of x equals 100, showing you that that's the signal. So to start, we're going to declare a couple of variables that will make our lives easier in the future. First, we have our sampling frequency. So we are going to set this to be about 1000. And this is the number of samples that we take per second. We're also going to define the period, which is the inverse of the frequency. And then we're also going to define a length of a sample. So we're just going to arbitrarily set that to be 1500. And then we're going to create our time vector. And so this is set to be a vector that goes from 0 to the length minus 1. We multiply that by the period. So now that we have these parameters, we can then construct a signal. And so these values are just completely arbitrary, but what we're going to do is we're going to set up a couple frequencies, couple sine waves, and then we're going to add some noise to it to make it a little muddy of a signal. So this first signal, is going to be a sine wave, and we're going to set this out to be 2 times the unknown frequency times pi times time. And so we know from algebra that this format gives us a signal where the frequency is, of course, the unknown frequency. I'll name this signal 1 because we're going to add a second signal into there too. Unknown frequency 2 is going to be 350 hertz. And then signal 2 is going to be the same as this, except with our second frequency. And just for kicks, let's multiply this by an amplitude of 0.7 to make it a little smaller. And then last but not least, we're also adding in some noise just to make our lives harder. So what this is doing here is it's creating a random signal amplitude of 2. And we're going to make it the size of the time vector. And so this is going to make our signal that when we plot it out to be virtually unreadable to our eyes. So let's plot out the first 50 points in our time vector and our vector of x, which I have not defined yet, so let's go and define that really quickly. And x is going to be the sum of the 3 signals that we created. So let's go ahead and run this. Oops, getting an error. Oops, this is called time, not t. Trying that again. So you can see our signal throughout time looks just about like nothing. We cannot see anything useful here. So what we're going to do that is create a fast Fourier transform that allows us to see the underlying frequencies of that. So this gives us the two-sided Fourier transform, and this is going to return a complex vector. If you've taken, for example, BioE 205 or a couple ECE classes, I know go pretty in-depth into it, you're going to get a real and imaginary component. We are only interested in the real component because that's all that matters to us for this application. So we're going to take the absolute value of the transform, and then we're just going to scale it by the length of the vector. And so important to note, this is still a two-sided Fourier transform, so this is going to be a big old mirror image of itself. And since we only need the first half of it to get useful information, we're going to make another vector called P1, which is the single-sided Fourier transform, and set that equal to P2 from L over 2 plus 1. And since this could possibly return a decimal point, and that's not good for MATLAB indexing, you can't have the 10.5 index of a vector, we're going to use this floor command to make sure that doesn't give us a decimal point. Now, obviously, since in this example it's going to be even, in the future when we're using audio files, we can't really control the number of samples, so that's a good safety measure to ensure that nothing goes wrong. And then we are going to scale it up a little bit. Because we're only taking half of it, we can double the amplitude. 2 times P1. And this is some fancy syntax and kind of jargon for our cases, but this exact code right here is taken straight from the MATLAB's documentation page for the fast Fourier transform. So if you're confused onto why we use any of these and you're interested in learning more about it, that's where I would direct you. So now that we have our single-sided Fourier transform, all it's left to do is define our frequency spectrum, which is our above sampling frequency times the range between half of the length divided by the length. Again, this is the syntax taken directly from the MATLAB page on this. Great, so here's our frequency spectrum. And now all it's left to do is create another figure, and we're going to plot the spectrum and our single-sided Fourier transform. So let's run this code again. And you can see we have spikes at our frequency values of about 200 and about 350. Great, so now that we have this done, let's move on to a practical example. Okay, so to start this exercise, make sure that you have this note.wave file downloaded. You'll be able to find a link to download it in the description of this video. And make sure that you place it in the same directory where you have your script, or else MATLAB is not going to be able to find it. And so to start this off, we're going to show you how to read an audio file. Then we're going to have the video pause and see if you can go through and solve it using similar techniques that we did last time. And then after that, we'll show you the solution and talk through a couple of the changes we had to make. And then after that, we'll be able to find the underlying frequencies within this note. All right, so the first thing we're going to do is just show you guys how to read a file. You may remember this from BioE 100 if you've taken it with Dr. Andrew Smith. We had to do this. And what this does is reads our note file into MATLAB. And so this this matrix X here is going to store the data inside of the wave file, and this frequency is going to be the sampling frequency of the wave file. And so using that, just running this really quickly, you can see this is a matrix that has 2 columns and then a lot of rows. And this is because a wave file has 2 audio channels, so it can, one channel for the left ear, one channel for the right ear. But since this was processed in mono, the channels are identical to each other, so we don't really have to worry about that. In wave files such as songs, where the channels will not be equal, there's ways you can combine it, such as taking the mean or just doing them separately. But for our purposes, we will not have to worry about that. So what we're going to do is use this command right here, which basically says we're just only going to worry about the first column of X. So from this point forward, please pause the video and try the exercise on your own. And we will check back in to show you the answer and talk about the modifications we've had to make. Okay, so hopefully you were able to get most or part of this exercise done. If you got all the way, congratulations. Now we're just going to talk through some of the changes we had to make. So first and foremost, we have to make our length just the length of the vector here. We can't make that just, an arbitrary length because we actually know the length of the sample here. So we're just going to use this argument right here to find the length of our vector. And then if we ignore this part right here really quickly and run it, you can see this code through time is not helpful. So we need to increase this range to 500 to see anything useful because we have a very high sampling frequency. We have a lot of waves. And so over here you can see now there's a bunch of different waveforms with different frequencies. Not very useful to the human eye, kind of cool to look at. And chugging along forward, we can see in the last line, and this is one of the places that many people might get a little stuck, the very last line of code returns a graph that is completely useless. We cannot see anything on it. And so this is because the frequency spectra is based upon the length of the input vector. And so if we put in a vector with a length of 81,000, the frequency spectra is going to be very long. And since we know we're not looking for signals that are in the range of 80 kilohertz, we're just going to take the first 1,000 data points in these vectors, and this will show us the relevant information we're looking for. So if we look in here, you can see we have a spike at x is 311. So at a frequency of 311 hertz, we have a spike. At a frequency of 370 hertz, we have a spike. And last but not least, at 466 hertz, we have a spike. So if you go online and use a frequency to note converter, you can see that that is in fact a D sharp chord. So the notes, I believe, are, let's Google that really quickly. Haven't taken music theory in a while. So those notes right here would be D sharp, F sharp, and A sharp. And those are indeed the notes that are found within this audio file. So I hope this was helpful for you guys. Please send any of us an email if you have any questions on the syntax or any of the processes used here. And thanks for watching.
So for the third challenge, we're going to do a physics type problem involving projectile motion. So for this problem, you have a projectile with initial velocity of 50.75 meters per second, and it launches at an angle of 5 pi over 12 radians. You're given that the initial horizontal and vertical positions of the projectile are at 0 and 0 for both y and x. So I want you to try plotting the graphs of y of t versus t and x of t versus t in two separate graphs in order to represent the vertical and horizontal motion of the projectile. For your time, you can use the vector 0, 0.1, 10 to represent the time in seconds. And be sure to include appropriate graph and axis titles. You can use the following equations in order to get the graphs of the horizontal and vertical motion. They're listed below. So I want you to take a couple minutes, pause the video, and try to solve this by yourself in MATLAB. Okay, so now for the solution, the first thing you want to do is start by defining your variables so that you know what you're working with. So you have your time, which you were given the vector for. You have Earth's velocity, which is g equals 9.8. v0, as you were given, was 50.75, and theta 0 was 5 pi over 12. Your initial positions were 0 and 0, and then you also want to put in your equations for both y and x into MATLAB. And then you can graph your equations from there. And since we're plotting x and y separately, we'll break them down. So we'll start with x. And you're creating a figure, so in order to plot the graph, you're going to use the function plot, and then you're going to do t comma x for your x and y axes. And then you can also add a title and labels to each of your axes, so you know what each of these are representing. So for title, you can use the function title and then put your title that you want in quotes. So for mine, I chose x of t versus t. And then for the labels, you can use time for the horizontal one, and then horizontal distance for your y-axis. And then you're going to do the same thing with y of t versus t. So for my title, I chose y of t versus t, and then for the x label, I used time, and the y label is altitude because that's showing how high your projectile is at that time. So yeah, that's how you would graph two different functions in MATLAB.
Okay, so in this challenge, what we're going to do is that we're going to visualize the COVID-19 data. So in this challenge, what we're going to do is that we're going to first import the data into MATLAB, and then we're going to plot the data onto a world map. And then last, we're going to add a slider to the figure so that we can control which state of the data we're going to plot. So you should see a link in the description to the CSV file, and you can download it and think how you can approach this problem. And then we're going to show how we are going to solve this problem. Okay, so let's first just check how does the CSV file actually look like. You can just open it using Excel or other software. So the first two rows of the data set is the province and the country. So you can see that here, some of the countries has the province data. So which is one thing we should look after later. And also on the third and fourth column is the latitude and longitude data. And all the columns following it is the case numbers related to each state. So what we can do in MATLAB is that first we can just use the read table function to read the CSV file. And then what we're going to do is that we're going to rename every column of the table. So we can just set its name using the first row of the data set. So we can just do data.properties.variable names and set it to the first row of the table. And then we can just delete the first row of the table. So you can see from the data here that after processing it, so the name of each column is changed into its proper form. And then what we're going to do is that we're going to characterize the country label, because we already mentioned that some of the countries are duplicated. So what we want to do is that we're going to give the same color to the same country. So what we can do here is that we're going to categorize the country region column, and then we're going to give its value to country. Next step we're going to do is that we're going to create a figure, and then we're going to use the GeoBubble function inside MATLAB. So the GeoBubble function, it takes the latitude and the longitude data, and then it's going to draw a circle on that location, which is with its size also taken as input in the function. So we want the size of the table, want the size of the circle to be proportional to the case numbers inside that country. We also want to set the colors in we also want to give the same color to the same country. So we can just use the category data we just used before. So we can just run the code now and see what happens. Okay, so this is our graph. It looks pretty nice, but we still haven't added the slide bar yet. So adding a slide bar is also very easy. You can just use the UI control function inside MATLAB. So you're going to set its parents to F, which is the figure. And also you want to set its position, which is labeled here. And also you want to set the minimum and maximum value of the slide bar. So also we want to add two captions on left and right of the slide bar so that the user can know what is the minimum and maximum date of the graph. So we want to set the left as January 32nd. We want to set the right as April the 11th. And the most important thing about the slide bar is the callback function. So the callback function will be called every time the value of the slide bar is changed. So we're going to create an anonymous function here using the symbol here. And then it's going to take the value, which is the object of the slide bar. So what we're going to do here is that we're going to call GeoBubble the second time, and we're going to change the value, the size of the circle into the proper date, which is the value of the sidebar object. And nothing else is going to be changed. So we can just change the sidebar value here. And then we can see that the values is going to change. So this is a pretty nice visualization project. You can just keep editing the code and see what you can do further. Okay, so I hope you guys think it's a nice challenge.